You're here because you want to really get graph theory, right from the basics.
Exactly.
Not just skimming the surface, but a proper deep dive into the fundamentals.
Uh-huh.
Think of it like building a really solid foundation because, well, the stuff that comes later in graph theory. It's fascinating, but it often builds right on these core ideas.
Absolutely crucial.
So today, our focus is super clear. Just an introduction to graphs.
That's the plan. We're working from this module, GT Module 1.pdf,
Right.
and our mission, if you will, is to really unpack the basic definitions, look at some key applications, why this stuff actually matters, and nail down the core concepts.
Like getting ready for a test on it.
Pretty much. By the end, you should feel totally comfortable with these foundational principles. We're going to go through it carefully.
All right, let's jump right in then. When we talk about a graph here, what are we actually talking about? It's not a bar chart, is it?
Huh. No, definitely not a bar chart. Formally speaking, a graph, usually called G, is defined as an ordered pair. G, V,
V and D?
okay, where V is just a set of things we call vertices, and E is a set of edges. And the key thing is, each edge in that set E connects an unordered pair of vertices from V.
Unordered pair.
Yeah, meaning the connection between, say, vertex 1 and vertex 2 is the same as the connection from vertex 2 to vertex 1. The edge just links them.
Okay, so vertices are like the points, the nodes.
Exactly. They could be anything: cities, people, computer components, and the edges are the relationships or connections between them.
So if we have an edge, let's call it E, connecting V1 and V2. What do we call V1 and V2 then?
Those are the end vertices for that edge E. They're the 2 points the edge links together.
Got it. End vertices.
Now, graph theory has some interesting twists. For instance, you can have an edge that actually starts and ends at the same vertex.
Really? How does that work?
It's called a self-loop. The module figure 1.1 shows one, like E1, that just loops back onto the vertex it started from.
A self-loop. Okay, connecting a vertex to itself. What else? Any other unusual connections?
Yeah, we can also have what are called parallel edges.
Parallel edges.
That's when you have 2 or more distinct edges connecting the exact same pair of vertices. Again, figure 1.1 shows this with E4 and E5. They both connect the same 2 vertices.
Ah, like having 2 different roads between the same 2 towns.
Precisely. Great analogy. The towns are vertices. Each road is a parallel edge.
Okay, so we've got self-loops and parallel edges. The module then mentions simple graphs. What makes a graph simple?
A simple graph is basically a graph without those complications. No self-loops and no parallel edges. Just one unique edge, at most, between any pair of vertices.
Cleaner, easier to start with.
Generally, yes. A lot of foundational results are first explored in simple graphs.
Now, something that could trip people up, especially if they're aiming for that test level, understanding the module lists a whole bunch of alternative names. Why so many terms for graphs, vertices, and edges?
That's a really good point. It reflects how graph theory pops up all over the place. Different fields kind of develop their own language for the same core ideas.
Oh,
So yeah, for graph, you might see linear complex or one complex. For vertices, nodes is super common, especially in computer science.
yeah, I've heard nodes.
Yeah, or junction, point, even zero cell. And for edges, you get branches, lines, elements, arcs.
Wow, okay.
It looks daunting, but they all map back to the same V and E idea. We'll try to stick mostly to graph, vertex, and edge here to keep things clear.
That definitely helps. Okay, so we have the basic building blocks. But why should we care? Why spend time on this? The module brings up some classic applications, starting with the Königsberg Bridge problem. Can you walk me through that one?
Oh, the Königsberg Bridge problem. It's like the historical origin story for graph theory, almost. Back in the 18th century, the city of Königsberg had this river, the Pregel, running through it.
Okay.
And there were 4 main land areas, islands and banks, and connecting these land areas were 7 bridges. The big puzzle everyone talked about was, could you start somewhere, walk across each of the 7 bridges exactly once, and end up back where you started?
Sounds like a fun challenge for a Sunday walk.
Totally. But it stumped people. Then along comes Leonhard Euler, the mathematician.
The famous
The
Euler.
very one. And he had this brilliant insight. He realized the exact shape of the land or length of the bridges didn't matter at all.
Just the connections.
Exactly. He abstracted it. He represented each of the 4 land areas, A, B, C, D, in the module's figure 1 to 4 as a vertex.
Yeah.
And each of the 7 bridges became an edge connecting the corresponding vertices. Figure 1 to 5 shows this graph. That move from physical layout to abstract connections was key.
So he turned the city map into a graph. What did he find out? Could you do the walk?
He proved mathematically that it was impossible.
Impossible. Why?
His reasoning used an idea we now call the degree of a vertex, basically, how many edges are connected to it.
Ah, the number of bridges touching each land area.
Precisely. Euler showed that for such a walk to be possible, what we now call an Eulerian circuit, every single vertex in the graph must have an even degree, an even number of edges connected to it.
And in Königsberg?
In the Königsberg bridge graph, all four vertices had an odd degree. I think it was 3, 3, 3, and 3, if memory serves.
So none were even.
Right. And because of that, Euler proved the walk was impossible, no matter where you started or which path you tried. A really powerful early result showing how structure limits possibilities.
Wow, so the connections themselves made it impossible. That really shows the power of this graph approach. What's another example? The module talks about the utilities problem.
Another classic. Imagine you've got three houses, H1, H2, H3.
Okay.
And you need to connect each of them to three utilities, say water, W, gas, G, and electricity.
Right, standard setup.
But here's the catch. You have to lay the pipes or wires so that none of them cross each other. Can you do it on a flat plane?
Sounds tricky. Trying to picture that. 3 houses, 3 utilities, 9 connections in total, no crossings allowed. How does graph theory help here?
Well, just like with the bridges, we abstract it. The houses, H1, H2, H3, and the utilities, WGE, become the vertices. That's 6 vertices in total.
Makes sense.
And each required connection, like water to house 1, gas to house 2, etc., becomes an edge. So we have 9 edges connecting the house vertices to the utility vertices.
Okay, a graph with 6 vertices and 9 edges. The question is, can we draw it flat without edges crossing? Figure 1.7 shows this graph, right?
Exactly. That specific graph structure is actually quite famous. It's called K33. K33. It's a type of bipartite graph, which we'll get to.
And the answer, like Königsberg, is impossible.
Correct. Again, it's mathematically proven that K333 is non-planar. You simply cannot draw it on a flat surface without at least one pair of edges crossing over each other.
Fascinating. So graph theory proves this layout puzzle is unsolvable without crossings. Real-world implications there for things like, I guess, circuit board design.
Absolutely. Anywhere you need to lay out connections without them interfering, understanding planar graphs is crucial. The module also briefly touches on electrical networks.
Right. How does graph theory apply there?
It's a very natural fit. In electrical circuits, the points where components connect the junctions, they become the vertices. And the wires or components connecting them, the branches, become the edges. Analyzing the structure of this graph, its connectivity, cycles, etc., helps engineers understand current flow, voltage, potential failures, the whole network's topology.
So the circuit diagram is essentially a graph ready for analysis. Makes perfect sense. The last application mentioned is a seating problem. 9 club members.
Yeah, this one's more about arrangements, combinatorics. You have 9 members who lunch together at a round table.
Okay.
They have this rule. Every time they meet, each person wants to sit between 2 different neighbors than they had at any previous lunch.
Ah, keeping things fresh. So the question is, how many different ways can they arrange themselves like that?
Exactly. How many distinct sets of neighbor pairings are possible?
And how does graph theory model this? The relationship is sitting next to someone.
Precisely. Each member is a vertex. 9 vertices. If 2 members sit next to each other, draw an edge between them. Since it's a round table, any valid seating arrangement corresponds to a cycle graph with 9 vertices.
The 9th cycle.
The problem then becomes, how many distinct 9 cycles can you form using these 9 vertices, such that the set of edges, neighbor pairings, is different in each cycle? Figure 1 to 9 shows a couple of possibilities.
And what's the answer? How many unique neighbor pairings can they manage?
Graph theory tells us there are only 4 such fundamentally distinct arrangements possible, considering rotations and reflections.
Only 4 for 9 people.
Yep. After the 4th lunch, they'd have to repeat a set of neighbor pairings they've already had.
That's surprisingly restrictive.
Yeah.
Shows how graph theory can quantify these kinds of combinatorial problems too.
Okay, so those are some powerful applications. The module then shifts gears into different types of graphs. First up, finite and infinite. That seems straightforward.
Yeah, it's pretty much what it sounds like. A finite graph has a countable, limited number of vertices and a limited number of edges.
Like all the examples so far.
Exactly. An infinite graph, conversely, has either an infinite number of vertices or an infinite number of edges, or both. For most practical problems in introductory study, we're focused on finite graphs. Makes sense. Next is bipartite graphs. What defines bipartite?
A bipartite graph is one where you can split all its vertices into two completely separate groups. Let's call them V1 and V2.
Okay, two distinct sets.
Such that every edge in the graph connects a vertex from V1 to a vertex in V2. There are absolutely no edges connecting two vertices within V1 and no edges connecting two vertices within V2.
Like the utilities problem. Houses in one set, utilities in the other. Connections only go between the sets.
Exactly. That K33 graph was a perfect example. The connections only bridge the two partitions.
Can you give another example of where bipartite graphs might show up?
Sure. Think about matching problems, like matching job applicants to open positions. Applicants are one set of vertices, V1, positions are the other, V2. An edge exists if an applicant is qualified for a position. You wouldn't draw an edge between two applicants or two jobs.
Right, the relationships between the two types.
Got it.
Okay, moving on to incidence and degree. These sound important for describing connections at the vertex level. What's incidence?
Incidence describes the relationship between a vertex and an edge. We say a vertex V is incident to an edge E if V is one of the end vertices of P.
So if an edge connects V1 and V2, that edge is incident on both V1 and V2.
Precisely. And V1 is incident to the edge, and V2 is incident to the edge. The module gives examples like maybe edge E3 connects V1 and V2, so E3 is incident on V1 and E3 is incident on V2.
Okay, and degree. That sounds like a count.
It is. The degree of a vertex V, written as dV, is simply the number of edges incident on it. How many connections does it have?
Just count the edges touching it.
Almost. There's one key detail. Self-loops count twice.
Ah, why twice?
Because a self-loop starts and ends at the same vertex, so it kind of contributes two ends to that vertex's connection count.
Okay, so count incident edges, but double count any self-loops. The module gives examples like dv13, dv24,
Yeah.
and sometimes it's called valency.
Yep. Valency is another term you might see for degree. Same meaning.
Got it. Now, this leads to the handshaking theorem. Sounds friendly. What does it say?
Huh. It does sound friendly. It's a really fundamental result. It states that if you sum up the degrees of all the vertices in any graph, the total sum will always be exactly twice the total number of edges in the graph.
Always. Sum of all degrees equals 2 number of edges.
Always. The module shows an example. Sum of degrees is 3 plus 4 plus 3 plus 3 plus 1 equals 14. And if you count the edges in that example graph, there are 7. 14 is indeed 2 times 7.
Why does that work? What's the logic?
It's quite intuitive when you think about it. Every single edge connects two vertices, or connects a vertex to itself twice in the case of loop.
Right.
When we calculate the degree of a vertex, we're counting how many edge ends land there.
Right.
So each edge having two ends contributes exactly 1 to the degree count of its first end vertex and exactly 1 to the degree count of its second end vertex.
So each edge gets counted exactly twice in the total sum of degrees.
Exactly. Like every handshake involves two hands. So the total sum of degrees must be twice the number of edges.
Clever. Very neat. Okay, building on that, Theorem 1.1 talks about vertices with odd degrees. What's the key property here?
Theorem 1.1 states something maybe a bit surprising at first. In any graph, the number of vertices that have an odd degree must always be an even number.
Wait, the number of vertices with an odd degree is always even. You can't have, like, just one vertex with degree 3 and all others even.
Nope. Impossible. You can't have 3 odd degree vertices either. It has to be 0, 2, 4, 6, etc. Always an even count of them.
Why? How does that follow from the handshaking theorem?
It follows directly. We know the total sum of all degrees is even. It's 2 times the number of edges. Let's split that total sum into 2 parts. The sum of degrees from the even degree vertices and the sum of degrees from the odd degree vertices.
Okay.
The sum of any number of even degrees is obviously going to be even.
Right.
Since the total sum is even and the sum of the even degrees is even, the remaining part, the sum of the odd degrees, must also be even.
Okay, the sum of all the odd degrees has to be even.
Exactly. And how can you add up a bunch of odd numbers and get an even total? Only if you have an even number of those odd numbers. 1 odd number is odd, 2 odd numbers sum to even, 3 sum to odd, 4 sum to even.
So you must have an even quantity of odd degree vertices for their degrees to sum to an even number. That's elegant.
It is, isn't it? A really fundamental property.
Okay, so this helps us check if a sequence of numbers could even be the degrees of a graph. The module gives steps for checking this. How does that generally work?
Right. Given a sequence of numbers, say 3, 3, 1, 1, can we draw a simple graph with these degrees? There are algorithms like the Havel-Hakimi theorem that provide a systematic way to check.
How does that work, roughly?
Typically, you'd sort the sequence first, usually descending, so 3, 3, 1, 1. Then you take the largest degree, which is 3. This means one vertex must connect to 3 others.
Okay.
So you remove that 3, and then you subtract 1 from the next 3 largest degrees in the list. So we subtract 1 from the other 3, the first one and the second one.
Well, 3, 1 is 2, 1, 1 is 0, 1, 1 is 0. So the remaining sequence is 2, 0, 0.
Okay.
Now you repeat, sort it, 2, 0, 0. Take the largest 2, remove it. Subtract 1 from the next 2 degrees. But we only have 2 zeros left. Can't subtract 1 from 2 degrees if we only have 2 degrees total, and they are 0. Wait, let me rephrase that. We need to subtract 1 from the next 2 degrees. Here, D2. We need to subtract 1 from the next 2 degrees, 0, 0. So we get 0, 1 and 0, 1, and therefore 1 is 0, 1. If you end up with negative numbers, or if at any step you don't have enough remaining degrees to subtract from, the original sequence wasn't graphical. Let's rerun that. Sequence 3, 3, 1, 1, N4, max degree is 3, which is N1, 1, 3. The sum is 8, which is even. Okay, algorithm, 3, 3, 1, 1. Take 3. Reduce next 2 degrees by 1, 0, 1, 1, 1, 1, 1, 1. And that's 2, 0, 0. Now sequence is 2, 0, 0. Sort. 2, 0, 0. Take 2. Reduce next 2 degrees by 1. More 1, 1, 1, 1, 1, 1, 1. We got negative degrees. So 3, 3, 1, 1 is not graphical for a simple graph.
Ah, okay, so that iterative process tells you if it's even possible. And if it is possible, can you actually draw it?
Yes, these algorithms are often constructive. The steps you take to verify it can often be reversed or adapted to show you how to connect the vertices to achieve those degrees.
Right, let's really nail this down with the examples from problem 5. First one, 1, 1, 2, 3. Can a simple graph have this degree sequence?
No. First check. The sum of degrees. 1 plus 1 plus 2 plus 3 was 7.
Odd number.
Exactly. The handshaking theorem says the sum must be even, so impossible for any graph, simple or not.
Easy check. Okay, next. 2, 2, 4, 6. Simple graph possible.
Let's see. Sum is 2 plus 4 plus 6, 14, even. So that's okay. But it's a sequence for n4 vertices.
Right.
What's the maximum possible degree in a simple graph with 4 vertices?
It's n1, so 4, 1 equals 3.
Exactly, but this sequence has degrees of 4 and 6, which are greater than 3.
So it fails the maximum degree check for a simple graph.
Correct. Not possible for a simple graph.
Okay, next sequence. 1, 3, 3, 4, 5, 6, 6. That's n of 7 vertices. Possible for a simple graph.
Let's think. Sum is 1 plus 3 plus 3 plus 4 plus 5 plus 6 plus 6 plus 6 equals 28. Even. Okay, max degree is 6. For NE7, max possible degree is N1 equals 6. So that's okay too. But look closer.
What is it?
We have 2 vertices with degree 6. In a simple graph with 7 vertices, a vertex with degree 6 must be connected to every other vertex.
Right.
If we have 2 such vertices, let's call them V6A and V6B, both are connected to all other 5 vertices. Consider any one of those other 5 vertices. It must be connected to V6A and it must be connected to V6B.
So those other 5 vertices must have a degree of at least 2.
Minimum degree of 2, yes. But look at our sequence. It includes a vertex with degree 1.
Ah, that contradicts the consequence of having 2 degree 6 vertices.
Exactly. So this sequence 1, 3, 3, 4, 5, 6, 6 is not graphical for a simple graph due to this structural implication.
That's a subtle one. Good catch. Last one from problem 5. 1, 1, 1, 1. Simple graph.
Let's check N4. Sum 1 plus 1 plus 1 plus 1 plus 1 plus 4 even. Okay. Max degree is 1. Is 1 on 1 equals 3. Yes. No obvious contradiction.
So this one looks possible.
Yes, this one is possible. You can draw it easily. Just 2 separate edges. Vertex A connected to B and vertex C connected to D. 4 vertices, each with degree 1.
Okay, that makes sense. Working through those really helps clarify the rules. The module then defines a regular graph. What's that?
A regular graph is simply one where every single vertex has the exact same degree.
Ah, uniform connections everywhere.
Precisely. If every vertex has degree k, we call it a k-regular graph. So a 3-regular graph means every vertex is connected to exactly 3 others. Regular graphs often have nice symmetries.
Okay, then we have specific vertex types. Isolated and pendant. What's the difference?
An isolated vertex is one with degree 0. It has no edges connected to it at all. It's just sitting there by itself in the graph's vertex set.
Completely disconnected.
Yep. A pendant vertex, sometimes called an end vertex, is one with degree exactly 1. It's connected to just one other vertex, like a leaf on a tree branch.
So isolated is degree 0, pendant is degree 1.
Got it.
And a null graph.
A null graph is a graph that has 0 edges. It's just a collection of vertices with no connections between them.
So all vertices in a null graph are isolated.
Exactly. By definition, if there are no edges, no vertex can have a degree greater than 0. The module shows an example, a null graph of 6 vertices, just the 6 dots. But remember, a graph must have at least one vertex.
Right, V can't be empty. Okay, now shifting to paths, circuits, and this idea of isomorphism. Isomorphism sounds like deciding if two graphs are fundamentally the same, even if they look different.
That's exactly the idea. Two graphs, G and G, are isomorphic if you can essentially relabel the vertices and edges of G to perfectly match the structure of G. There's a one-to-one correspondence between their vertices and edges that preserves all the connection relationships. Incidents.
So they have the same connection diagram, just maybe drawn differently or with different labels.
Yeah.
What tells us they might be isomorphic? What properties must they share?
Well, there are necessary conditions. If two graphs are isomorphic, they must have the same number of vertices.
Okay, that makes sense.
They must have the same number of edges.
Also makes sense.
And they must have the same degree sequence. If you list the degrees of all vertices in G, you should get the same list of numbers, maybe rearranged, as the degrees in G.
Same number of vertices, same number of edges, same list of degrees. If all those match, are they definitely isomorphic?
No, that's the crucial point. These are necessary conditions, but not sufficient. Just because they match on these counts doesn't guarantee they have the same structure.
Okay, need to remember that. Let's look at the module's examples. Example 1, G1 and G2. Both have 5 vertices, 6 edges, and the degree sequence, 3, 3, 3, 2, 1. Are they isomorphic?
Well, they satisfy all the necessary conditions we just listed. Same number of vertices, edges, and the same degree sequence. So there could be isomorphic. It's strong evidence, but to be certain, you'd need to check the actual connections.
Example 2, G1 and G2. Both have 8 vertices, 12 edges, and every vertex has degree 3, so they're 3 regular. Isomorphic.
Again, all necessary conditions met. 8 vertices each. Same degree sequence. All threes. Handshaking confirms 12 edges. 8, 3, 2 equals 12. For regular graphs, matching these often means they are isomorphic, but again, not a 100% guarantee without checking structure. Very likely, though.
Example 3, G1, G2, G3. All have 10 vertices, all are 3 regular, isomorphic to each other.
Same reasoning. 10 vertices, all degree 3. That means 10, 3, 2 equals 15 edges each. They satisfy the necessary conditions. It's highly probable they are all isomorphic representations of the same 3 regular graph on 10 vertices.
Okay, now example 4 seems to be the counterexample. G1 and G2. Both have 6 vertices, 5 edges, and the same degree sequence, 3, 2, 2, 1, 1, 1, 1. But the module says they are not isomorphic. Why not?
This is where we see why the conditions aren't sufficient. We need to look deeper. In G1, find the vertex with degree 3. Check the degrees of its neighbor.
Okay.
Now do the same in G2. Find the vertex with degree 3, check the degrees of its neighbors. If the graphs were isomorphic, the neighborhood structure around corresponding vertices should also match up.
What's different here?
The module explains that in G1, the degree 3 vertex is connected to 2 vertices of degree 1, pendant vertices. But in G2, the degree 3 vertex is connected to only 1 vertex of degree 1.
The local connections around the highest degree vertex are different.
Exactly. Since the neighborhood doesn't match, even though the overall degree sequence is the same, the graphs cannot be isomorphic. You can't relabel G1 to make it look like G2.
That's a really important point. Look at the neighbors' degrees, too. Okay, next concept, subgraphs. What's a subgraph?
Pretty intuitive. A graph G is a subgraph of a graph G if all the vertices of G are also in G and all the edges of G are also in G, and the edges connect the same vertices in both. You basically get G by deleting some vertices and/or edges from G. Notation is GEG.
So it's just a piece of the original graph.
Yeah.
Any key properties?
Yeah, a few basic ones. Every graph is its own subgraph. A subgraph of a subgraph is still a subgraph of the original. A single vertex is a subgraph. A single edge plus its 2 end vertices is also a subgraph.
Seems straightforward. Now, edge disjoint versus vertex disjoint subgraphs.
Edge disjoint subgraphs are 2 or more subgraphs that don't share any edges. They might share vertices, but their edge sets are completely separate.
Okay, no common edges.
Vertex disjoint subgraphs are stricter. They don't share any vertices, and if they don't share vertices, they obviously can't share any edges either. So vertex disjoint implies edge disjoint.
Got it. Completely separate pieces for vertex disjoint. Okay, now let's talk about moving through a graph. Walks, paths, and circuits. What defines a walk?
A walk is a sequence, alternating between vertices and edges, like V1, E1, V2, E2, V3, starting and ending with a vertex. The rule is that each edge in the sequence must connect the vertex before it to the vertex after it.
Can you repeat things in a walk?
You can repeat vertices as many times as you like, but typically a walk definition doesn't allow repeating edges. The module gives an example. V1, V2, B, V3, C, V3, D, V4, E, V2, F, V5. Notice V3 and V2 are repeated, sometimes called an edge train or chain.
And the first and last vertices, V1 and V5 in that example.
Those are the terminal vertices of the walk.
What makes a walk closed versus open?
Simple. A closed walk starts and ends at the same vertex. An open walk starts and ends at different vertices.
Okay. Now, how is a path different from a walk?
A path is a more restrictive type of walk. It's an open walk where no vertex is repeated.
No repeated vertices at all.
Exactly, which also means no edges can be repeated either. So that example walk V1 of V2, V3, V3 could not be a path because V3 was repeated. But maybe V1 of V2B, V3D, V4, if those vertices are all distinct, that would be a path.
How long is a path?
The length is just the number of edges in it. The path V1 of V2B, V3D, V4 has length 3.
And can self-loops be in paths?
No, because a path can't repeat vertices and a self-loop inherently starts and ends at the same vertex.
Right. So a path is a simple, non-repeating journey between two different points. What about a circuit?
A circuit or a cycle is basically a closed walk where no vertex is repeated, except for the start-end vertex, which naturally appears twice.
So like a path that loops back to the start without crossing itself?
Exactly. Think of a triangle or a square shape in a graph. That's a circuit. The module also calls them elementary cycles, circular paths, polygons.
What about the degrees of vertices within a circuit?
Every vertex in a circuit must have a degree of exactly 2, considering only the edges of the circuit itself. One edge coming in, one edge going out as you trace it.
Is a self-loop a circuit?
Technically, yes, a self-loop fits the definition of a circuit of length 1. But most circuits involve multiple vertices and edges.
Okay, so summary. Walk allows repeated vertices, but usually not edges. Path is an open walk with no repeated vertices. Circuit is a closed walk with no repeated vertices except start-end. Great. Now connectedness. When is a graph connected?
A graph is connected if you can find at least one path between any two distinct vertices in the graph.
Yeah.
Basically, it's all one piece. You can get from anywhere to anywhere else by following edges.
What about null graphs? Are they connected?
A null graph with only one vertex is usually considered connected, vacuously, but a null graph with more than one vertex is disconnected because there are no edges, hence no paths between the vertices.
And if a graph isn't connected?
We call it disconnected. It means the graph is made up of 2 or more separate connected pieces. Each of those pieces is called a connected component or just a component.
Like islands of connectivity.
Exactly. The module shows examples of disconnected graphs with multiple components.
Theorem 2.1 gives another way to think about disconnected graphs using partitions. Can you explain that?
Sure. Theorem 2.1 says a graph G is disconnected if and only if you can split its vertex sets V into 2 non-empty disjoint subsets, V1 and V2, such that there's no edge connecting a vertex in V1 to a vertex in V2.
So you can slice the graph into 2 pieces with no connections between them? That seems equivalent to being disconnected. How does the proof work?
It goes both ways. If you can make such a partition, V1, V2, then pick any vertex U in V1 and V in V2. There can't be a path between them, because any path would eventually need an edge crossing from V1 to V2, and we've said no such edges exist, so the graph is disconnected.
Makes sense. And the other way?
If the graph is disconnected, then there must be some pair of vertices, A and B, with no path between them. Let V1 be all vertices reachable from A, including A. Let V2 be everything else, including B. Then V1 and V2 are non-empty and disjoint. Can there be an edge between some X in V1 and some Y in V2? No, because if there were, U would be reachable from A, go to X, then cross the edge to Y, but Y is in V2 specifically because it's not reachable from A. So no edges can exist between V1 and V2, thus a disconnected graph always allows such a partition.
That's a solid proof. Okay, Theorem 2.2 links odd degrees back to connectivity. What does it say?
It says if a graph, connected or not, has exactly 2 vertices with odd degrees, then there must be a path connecting those 2 specific vertices.
Why must there be a path between them?
It comes back to Theorem 1.1, even number of odd degree vertices. Suppose the 2 odd degree vertices, U and V, were in different connected components. Then the component containing U would have exactly 1 odd degree vertex, U itself. And the component containing V would also have exactly 1 odd degree vertex, V.
Right.
But each component is itself a graph, and Theorem 1.1 says every graph must have an even number of odd degree vertices. You can't have a component with just 1.
Contradiction.
Exactly. The contradiction forces us to conclude that U and V must be in the same connected component. And if they're in the same component, by definition, there must be a path between them.
Neat deduction. Lastly, Theorem 2.3 gives a limit on edges based on components. What's the gist?
It states that a simple graph with n vertices and k connected components can have, at most, nk plus 1, 2 edges.
nk plus 1, 2. Where does that come from?
Think about how to maximize edges in a disconnected graph. You want to put as many vertices as possible into one single component and make that component as dense as possible, ideally a complete graph, while leaving the other components as small as possible, like isolated vertices. The maximum number of edges occurs when you have one component with nk plus 1 vertices and k1 components that are just single isolated vertices. A complete graph on nk plus 1 vertices has nk plus 1 and k2 edges. The isolated vertices at 0 edges. Wait, let me recheck that formula derivation. Okay. Yeah, the maximum occurs when one component has nk plus 1 vertices and the other k1 are isolated. A simple graph with n vertices has at most n1 2 edges. So a component with nk plus 1 vertices has at most nk plus 1 nk2 edges. The formula given is nk plus 1 2. Let's reread the theorem text. Yes, it says nk plus 1 2. This bound is actually achieved when k1 components are isolated vertices and one component is a complete graph on the remaining nk1 and k plus 1 vertices. The number of edges in a complete graph, km, is mk1 2. Here nk plus 1. So edges nk plus 1 nk2. The provided formula nk plus 1 2 might be slightly off or interpreted differently. Let's stick to the idea. More components means fewer possible edges compared to a fully connected graph. The most edges happen when k1 connected, giving nn12 max edges. Disconnecting reduces this maximum.
Okay, the core idea is that being disconnected limits the total possible edges. Got it. Now let's really prep for that hypothetical test with these university questions. Question 1. Differentiate walk, path, circuit. Key distinctions.
Okay, quick summary.
Sequence of vertex edges. Vertices can repeat. Edges usually don't. Can be open or closed.
An open walk. No vertices repeat, so no edges repeat either. A circuit or cycle. A closed walk. No vertices repeat except the start 10 vertex is the same.
Perfect. Question 2. Possible to have a graph with 12 vertices, 2 degree 3, 10 degree 4. Justify.
Let's check the sum of degrees using the handshaking theorem idea. Sum always 2, 3 plus 10, 4 equals 6 plus 40 equals 46.
Is 46 even?
Yes, 46 is even. Since the sum of degrees is even, a graph with this degree sequence is possible. It would have 46 2 equals 23 edges. So yes, possible.
Good. Question 3. True that a simple graph with n vertices must be connected if it has more than n1, n2, 2 edges.
Yeah.
How?
Use the contrapositive like we discussed with theorem 2-3 or a related result. Assume the graph is disconnected. If it's disconnected, it has at least 2 components. The maximum number of edges a disconnected simple graph on n vertices can have occurs when one component is as large as possible, n1 vertices forming a complete graph, and the other is tiny, one isolated vertex.
Right.
A complete graph on n1 vertices has n1, 1, 2, and n2, 2 edges. The isolated vertex adds 0 edges, so a disconnected simple graph can have at most n1, n2 edges. Therefore, if your simple graph has more than n1, n2, 2 edges, it cannot be disconnected. It must be connected, QED.
Excellent. Last one, question 4. Prove if a graph has exactly 2 odd degrees, there's a path between them. We did this with theorem 2-2. Recap the proof.
Sure. Let the 2 odd degree vertices be U and V. Assume, for contradiction, they are in different connected components, say Q and CV.
Okay.
Then Q contains only 1 odd degree vertex, CV contains only 1 V. But theorem 1.1 says every graph, and thus every component, must have an even number of odd degree vertices.
So Q and CV having only 1 is impossible.
Exactly. This contradiction means our assumption was wrong. U and V must be in the same connected component.
And if they're in the same component?
By definition of a connected component, there must be a path between any 2 vertices within it. Therefore, there must be a path joining U and V.
Fantastic. We've really covered the ground here. Definitions, applications, types, degrees, handshaking, odd vertices, isomorphism issues, walks, paths, circuits, connectedness, components, and tackle those proofs. Feels like a very solid foundation now.
Absolutely. Anyone following along should have a much stronger grasp of these fundamental graph theory building blocks. It really sets the stage for understanding more complex graph algorithms and applications later on.
Definitely. So as a final thought to chew on, think about where else these ideas, vertices, edges, paths, components might apply. Beyond bridges and utilities, what other complex systems or maybe even social dynamics could be modeled and maybe understood better using this language of graphs?
That's a great question to ponder. The applications are incredibly broad.
We hope this deep dive has given you that solid footing and maybe sparked some curiosity to explore specific areas further. Thanks for joining us.